A Python notebook is an isolated playground. It works for iterating on experimental models, but deploying that same code into a highly concurrent, multi-node cloud environment causes the architecture to fracture under the weight of real-time data. Deploying machine learning models without rigorous data lineage and observability tracking every step of inference makes the system opaque. Latency spikes go unnoticed, redundant compute queries drain budgets, and the system fails the moment it attempts to interact with the physical layer. Solving these specific failures in high-velocity neurotelemetry requires a 12-layer pipeline architecture designed for simultaneous signal acquisition and processing. This maps a strict flow, starting at layer 1, staging raw signals, and routing through 12 processing layers, terminating at layer 12, the physical actuator. The challenge is translation and security, converting noisy analog telemetry into deterministic kinematics, while enforcing zero-trust hardware actuation. Understanding enterprise AI requires tracing a single data packet through this pipeline, from its asynchronous ingestion and semantic mapping to its final physical gating. The pipeline begins at the network edge with the acquisition of high-frequency raw EEG telemetry. Inside the ingestion module, the raw data stream hits a fast API endpoint. The data contract at this stage is rigid. Every packet must include a UTC timestamp, specific electrode position data, and the raw voltage streams. Pydantic schemas enforce this contract at the gate. If a payload is malformed or an electrode ID is missing, the system rejects it instantly, preserving compute resources for valid data. Validated payloads move from the API into a dedicated asynchronous memory buffer, like a Redis or Kafka queue.
This buffer manages 1000 Hz telemetry without blocking the API or dropping critical packets, decoupling incoming biological signals from downstream processing speeds. Establishing an asynchronous validation gate at the edge prevents downstream data corruption in high-velocity physical systems. Once the raw data is validated, it enters the transformation layer to be converted into a queryable state. This is managed via a DBT pipeline. The Directed Acyclic Graph, or DAG, traces the dependencies from staging raw telemetry to intermediate cleaning and final metric aggregation. During the staging process, nested JSON payloads are mapped into flat, queryable tables inside a Postgres database. The intermediate stage applies logic to the data, normalizing amplitude and identifying physical artifact spikes such as eye blinks to ensure signal integrity. This clean data enables the next stage of the pipeline, MLOps compute optimization. By auditing the DBT lineage, the system implements incremental delta processing logic. This avoids full database scans by only processing the signals that have changed since the last run. Transitioning to incremental processing protects pipeline resiliency and reduces enterprise cloud warehouse spend by up to 80%. Cleaned mathematical data remains an abstraction until it is mapped to a specific physical intent. The pipeline converts the cleaned metrics into a 512-dimension vector array. This embedding is generated directly from the specific frequency bands and raw voltage streams processed in the previous layers. This vector array queries a Weaviate database to find the closest matching cognitive state. The system calculates cosine similarity to find the nearest neighbor in its indexed. The score identifies how closely the current brain signal aligns with a known motor pattern. The pipeline translates this mathematical match into a human-readable intent, such as the command to reach forward. High-speed vector search translates raw biological mathematics into actionable real-world context. Generating a semantic command is not enough for industrial use. Physical systems cannot actuate hardware based on an unverified inference. The SLRPD framework, covering security, legal, regulatory, privacy, and data, serves as the mandatory governance matrix for the pipeline. A message broker enforces this governance. An intent packet entering the unvalidated channel is immediately intercepted by a governor node. The governor node acts as a zero-trust hypervisor, stopping all execution requests for validation. It checks cryptographic passports and verifies physical hardware telemetry, including MAC addresses and GPS fences, ensuring the system is operating within a trusted zone. The logic agent is isolated. It only receives the execution payload if the governor node promotes the packet to a validated channel.
Zero-trust orchestration ensures that an AI model cannot trigger a physical action without cryptographically verified real-time hardware consensus. The logic governing this BCI pipeline addresses the core security vulnerabilities found in advanced manufacturing and digital twins. In a physical manufacturing environment, the BCI pipeline directly governs the precise movement of high-tech robotic systems. Enterprise companies use this telemetric architecture to prevent intellectual property theft and unauthorized production of high-value assets. The physical machine requires a telemetrically validated, single-use digital token from the governor node to power on and begin actuation. The moment sensors detect that the specific physical asset is finished, the system triggers a kill switch and the execution token is permanently burned. Without both a live, validated telemetry stream and an active digital token, unauthorized physical production is impossible. Ultimately, building auditable, secure, and highly efficient architectural pipelines is what safely binds digital intelligence directly to the physical world.